Okay, we're going to learn a few things that you would learn if you were actually working in the lab, but I want you to learn some of these techniques that'll really make you kind of savvy in the lab. So I'm going to start by showing you some dilution things. I want you to learn some little tricks of dilution, and then I want you to also understand the spectrophotometer. So that's the two things I really want you to get out of the actual seeing the lab procedure is, once again, how to properly do dilutions. And so the keys here are you're going to want to know how to, depending on what volumetric flask or pipette you're using, you need to know how to clean them. You need to know how to clean vials. And then the other part of it is I want you to understand the instrument over here, the spectrophotometer. So I have both spectrophotometers up here, so you can just compare and see, because this is older, but it's actually higher quality. It has some settings in there that help you really understand spectroscopy. This is a little less expensive, a little lower quality, but it's, it'll Bluetooth up with your phone, so it's a little different. But I want to just teach you a couple things. So let's get going. The first thing you do is you always turn on your spectrophotometers because you want the bulb to get lit up. So for these, they just plug into the USB ports on the computer, and then this one has a power button on. I'm going to show you how to turn this one on here in a second. But that's the starting point. Now I'm going to run to another camera here and show you how the software works. So we're going to turn on the older spectrophotometer first. It's the Ocean View, Ocean Optics. And the very first thing you'll notice when it's turned on, it'll look for the spectrophotometer. This one had already found it, so but you'll see it down here. You'll see that it identifies the spectrophotometer. But here's where you're going to really learn some stuff that's generally applicable to all your spectroscopy. So the first thing I'm going to do is I'm going to turn on the lamp. And when you look in the screen, when this originally turns on, it comes out as a very high intense peak. I'm going to move this out of the way so you can see. So you can kind of see the peak going up, and then it kind of flattens out completely as if it's really intense. So imagine that you had a camera and you were pointing it directly at the sun, and you had the iris way open, or if you looked at the sun, you'd have way too much exposure. So this is just getting way too much light through. So the intensity is running up the left-hand side, the y-axis, and the different wavelengths are running along the x-axis. So we're going to start with the short wavelength, which is actually high energy, and we're going to run out to the long wavelength, which is low energy. So this is just the visible spectrum, basically from 350 to about 1,000 nanometers. So the very first thing is we change the integration time. The integration time, when it lowers, it's like closing the shutter on a camera. It's like taking that camera and getting smaller and smaller. So when you see that, you can see the light intensity start to drop. All right? And the goal is, there's kind of a line in here. You want it to be at about 90%. There you go. And so that's an okay. So right now we have 35 milliseconds that the integration time is open. Now you can see, as you look at the light from the high energy, you have very little intensity. As you move to higher or lower and lower energy, or longer and longer wavelengths, you'll see different response at different wavelengths. So if you were just measuring based on what wavelength you are, you would have a different intensity at every wavelength. So this instrument's going to account for that, and I'm going to show you that, but just keep that in mind. That, for example, at 425 you have a lot of intensity. At 525 you have very little intensity. And the way you can think about that is you have a light that gives out all the colors of the spectrum, Roy G. Biv. It just gives them out at different intensities. And remember, the brightness of the light is what gives it a higher intensity. So this high energy wave right here has a lot of intensity, then this has a lot less intensity. But the instrument's going to have to account for that. Another thing you'll see in here is that there's a lot of noise. You see in the signal, there's a lot of, that's electronic noise. It's kind of vibrating up and down and bouncing up and down. So I'm going to teach you two things, and this is important. The lab asks about it, but I want you to understand that this is generally applicable to all spectroscopy. The electronics of the system, because your circuits are actually oscillating back and forth at 55 hertz. So every second there's been 55 oscillations. So it's very common that you have electronic noise. So what you want to do is you want to get kind of this ups and downs out of there. So what you can do is average scans. So as I start to move that up, so let's just move it up to 10 just to kind of make the point. Now you'll see what happens is the response is a little slower, but the ups and downs are kind of going away because the highs and lows start to average out. Then the next thing we have on here is called boxcar width. This is a very interesting concept. A boxcar kind of works like this. It's basically saying if you're reading this peak as you move along, the response just to this little white tip is going to be very much in line with every little up and down along the peaks, right? So if we said, well, what if we just, instead of just reading at that real fine point, what if we read something a little wider, like made the boxcar a little wider? So think of it like a train. And so instead, if I'm trying to read about where my thumb, or where the point is here, instead of just reading at that point, it reads way up and then way down all along the boxcar and say, well, what's the general trend? And when you start to do that, then these sorts of peaks here, it would ignore because it would say the general trend is up. Oh, there's a real peak. And it would feel that, and then as it goes down, it would start to, it would get rid of some of these big peak features in there. You just have to be a little careful with this. This is also sometimes called smoothing. But I'm going to run it up to about 10 to prove the point. And that'll be something I ask about in your, you know, on your online just lab technique evaluation. So look what happened, how we smoothed out the peak. If you overdo, you can make peaks go away. So you have to be careful. If the boxcar's too big, you know, if the boxcar was like the width of my arm, it would smooth out that full peak. So you have to be careful. I'll exaggerate. So you can see when you make the boxcar too big, you'll actually make peaks go away. So now I'm going to jump it back down to a reasonable number, about 10 again. And now those little electronic noise features are gone, but the major peaks remain. So this is a good way to do this. And now we're about ready to take spectrum. Now, we've got to eliminate the problem of, hey, we've got a high intensity peak here and a low intensity peak here, so that we can see where my sample reads. All right? So I'm going to show you that, how you eliminate that later after we prepared a little bit of solution. Now I'm going to jump over. So this one's kind of set up, and now if I wanted, I could even increase the intensity back up a little bit because the smoothing kind of knocked it down. Oh, don't overdo though, because see how that starts to flatten? That means you're reading too much. Actually, I'm going to drop that below 3500. Quite often these will have a line on them, but that's a good point. All right, so there's that one. I'm going to show you the other spectrophotometer. This is the Pasco. It's got a little bit different looking software. See if I can get it a little bigger here. It's kind of jumped around there. Okay, here we go. There we go. So one of the things I dislike about this is this rainbow color. So if you click this down here, it gets rid of it. All right, so now we're working on this other box, and I'll just jump cameras for a second so you can see what I'm talking about. Now we're working on this. The previous one I showed you was the red tide USB. which we call the Ocean Optics. That's the company. And then this is the Pasco. That's the company. It's newer, but it's a little less precise. Okay. So now we're working on the Pasco. So again, it has a lot less, or it's got a kind of like things taken care of. For example, that it automatically adjusts the light intake so it doesn't overdo. So one of the things you have to start with on this, I'm gonna see if I can turn it on here. So it's going to ask me to calibrate first. So we're going to go get our samples ready, and then we'll get back and work on this one for a second. So let's work on this concept for a minute. One of the keys to dilution, and just making simple samples, and you've done this before, but it's just such a simple idea, but I just want people to get it right, is, you know, I've got this glassware. Maybe I'm going to use this pipette. It's fresh out of the box. These are plastic, so we always use a brand new one, but you still may feel uncomfortable. You might want to clean it out first. You have these volumetric flasks. You have a little beaker. You have ultimately you have the cuvettes as well. So I'm going to start with this cuvette first off, and we'll talk about cleaning it for a second. So it's one of the things to understand about these is they have a little bit of groove to them, and that's just to save volume. So I can put my finger in there because the light, the business end, doesn't pass through this little indentation. That's just to save volume. But the important part, and you can look at it if you kind of see, you can see there's a really nice square flat piece of glass that goes on the wide sides. That is the optical glass. So what happens is you have a fairly inexpensive, like a polycarbonate body, and then you put some optical glass or plastic pieces on the side, and that's where the money is. That's what you don't want to handle with your hands. And if you do have to clean them, you can just get regular lens cleaning paper. And that's just what you'd use on your glasses because it doesn't scuff them up. Some people use Kim wipes. I don't recommend that because the Kim wipes are a little rougher as far as going to glass, and anybody who wears glasses understands that, because if you get something rough on your glasses, it kind of ruins that pair until you can get a new one. So we cleaned off the optical glass, so we'll keep that in mind when we're ready to run samples. So now let's talk about generally as you dilute, and then I'm going to give you a good idea here how you can do this. A little poetry for you. Okay, so here's the way I think of it. If I'm going to put what we call the mother solution. So the mother solution is the most concentrated solution. Everything below that would be the sons or daughters, right? The dilutions. But the mother solution is the most concentrated, and it gives way to the diluted offspring, so to speak. So, if you're just going to use the mother dilution directly, or if you have a pristine sample that's already prepared and you do not want to dilute it anymore, then what I say, if you're not going to dilute, then cleaning what you're going to put it into with solvent is pollution. It's not okay. On the other hand, if you're about to dilute the mother solution, then solvent is the route. So no dilution, solvent is pollution. Going to dilute, solvent is the route. That's the way I would say that. I'm kind of mispronouncing route, but it works for the poetry, I guess. Poetic license, that's what that is. All right, so here's what we're going to do. I'm going to take the one cuvette that I had actually just cleaned, and I'm going to just put some mother solution in there so I can look at the most concentrated. You can write on these cuvettes if you write up high, because like we just explained, this down here is where the business end is. All this up here will not show up. The light will not pass through any of this. The light actually passes through the bottom half. So I don't even have to fill solvent up above that half, where I just need to make sure I cover the optical glass. That's the key. So I'm going to mark that one M. And again, now I get to apply what I just said in that I'm like, okay, I'm just trying to put mother solution in there, so I'm not trying to dilute. So to pre-wash with water would be wrong, because I'll leave a little bit of drop of water in there, and that's going to dilute the mother solution I put in there. So this is the second one, or no dilution, solvent is pollution. So in that case, you just use the mother solution to rinse things out. Now, another thing is, you know, the whole class may be using this bottle, so I don't want to put something down in it and pollute it. So I'm going to use that same principle very quickly and going to go into this glass, give it a quick little shot. I can actually just rinse out this glass into my waste beaker. Give it another one. There you go. And I tilt it over, get it up on the sides. There you go. And now I actually have some mother solution. Now do you follow that principle I just showed you, where I said, hey, we're not going to dilute, so solvent would pollute. If I rinse with water, it would somehow dilute that. So I now know, because I'm not diluting, right, then the mother is the solution in that case, right? It's the way to do that. And so I can do that again in here in this little cuvette, because I want to just get this pure solvent in there. That's all I want. So rinse with what you're about to put in there. And these, if they're already clean, you don't have to do this much. But again, that's almost, I only used about 1.5 mils just to get above that point. So that's good. So there's my mother solution. So there we go. So that's waste. So now I'm going to do a dilution. I'm going to do a 1 to 10 dilution, for example. All right, so here we go. I'm going to take 1 ml of the mother solution. So now this vial is good to go. And I'm going to dilute it to a total of 10 mils with water. I.e., I'm going to add 1 ml of mother solution, and I'm going to add 9 mils of water. So now the mistake a lot of students make is they add 1 mil, and then what they do is they measure out 9 mils, but there's no point, because these volumetric flasks are very precise. They have a single line on here, and when you fill exactly to the mark, that's going to be 10. Now what we've learned with our graduated materials is we've learned when we have a graduated pipette or graduated cylinder, you know to use the last line that you see as accurate, then you go 1 mark beyond. So this one reads 5.1, 5.2, 5.3. So I would report 5.30. Now that's a problem here because there's only 1 line. So how do I know how precise that is? When I look on here, there's a plus or minus, and it says plus or minus 0.04. So now on that one, you can actually report this then as 10.00 when I get it directly to the mark. And the thinking there is it's very narrow up this neck. So if a lot of people, and this is actually what they do, is they do it by weight. They fill to the mark over and over and over, and they see where it varies. And this doesn't vary at 10. It doesn't vary, in other words, somebody measures in 10, someone measures 11, someone measures 9. It doesn't measure at 10.1. It measures at 10.00. That's why they have that plus or minus. And over the multiple measurements, what they saw, it ranged plus or minus 0.04. All right, so that's one of the keys to using these single line flasks, is you have to have the precision mark to tell you how much. So again, I need exactly 1 mil of mother solution. So I'm not diluting in here. So if I want to rinse this out, again, if I used water, I would have a problem because I might dilute what's about to come in there next. So again, the key is, first off, it's probably clean because it's brand new and these are disposable. But what you do is you bring up a little bit of solvent. You can turn it sideways, and sometimes it helps to just remove this so the fluid moves. And then you can move that fluid up the nozzle and move it around and rinse inside there. And that's going to be good. Blow that out. The pipette man. And now, the next trick of these is, these are mass produced. They're fairly inexpensive. They're disposable. You can always get the cylinder produced correctly. It's the little tip that gets you, because that's going to be inconsistent. So don't assume that this tip is part of the measurement. So if I want to deliver 1 mil, I'm not going to go to the 1 and spit it out, because that's probably inconsistent in that little part. And you'll see that in the calibration curve. So what I do is I go above. In other words, I'll draw up to 2 and then release down to 1, and then I've definitely delivered from 2 to 1. That's exactly 1 mil. And if I go up to 3 and drop down to 2, it's no big deal. Key is I just go past. Okay, I don't want to return that back to the pristine mother solution there. So I can do that on here. These are nice because they have a really controlled arm. See if I can get that. I want to make sure I'm getting that in the picture. Okay, yeah. So I usually control it down to the mark with my thumb on that little really fine wheel. And I can get it right to the mark. I look at it level. I don't look when my head's above the line or below. I look straight across to the line. I get it down to 2. There you go. Then I'm going to drop it right into the volumetric flask. Drop it down to the 1. Sometimes I got to pick that up to see it really good. Right to the line. I touch off the edge on my way out. Put the waste in here. Now for storage, always make sure these stay upright. Don't let them lay on their side, because if you let them lay down, sometimes the fluid drops back up into this pipette man, and then that's going to put contaminants up in there. So now that's a mil. So now I'm going to dilute to the mark. Now at this point, remember, do here when you're diluting to the mark is you can rinse in a little any of the droplets that are along the side when you're diluting to the mark. So this is a good chance to get everything off the edge on the way down. And then when I'm getting to that last line, if I use this bottle, I'm going to overshoot. So sometimes what I do is just dilute with a little water. Again, I can rinse with that, rinse with what I'm about to put in there. It's kind of that thought there, right? Okay, now I'm going to add water to the mark. That's where this comes in. It's a good way to add right to the mark. Sideways on it. The idea is that the bottom of the meniscus comes right to the line. So it's probably a little hard to see that, but the bottom of the meniscus is right to the line. Okay. Then we have these caps. Sometimes I might even go one additional. Take a little bit of my Kim wipe and make sure if there's any water hanging up there, I get it out, because I don't want that to wash down in there when I'm turning this over. Now I'm ready to mix. So you either put parafilm or you can put these glass stoppers. You can invert and start going around. I usually do an inversion quarter turn, inversion quarter turn till you got the full circle in. Make sure you get that all mixed up. That's another thing that students do from time to time, and I know it's a lot to remember, but sometimes they do all this, they do it exactly the mark, then they use it right away and it never had a chance to mix. So it's important that it mixes. Okay, so I'll keep track of this. Ready for a fresh one of these. Again, I'm going in here, so now I got to stop and think. I do not want this to dilute anymore, right? So no dilution. So if I rinse with water first, that's going to be pollution, right? What I want to rinse with is what I'm about to put in there. So the key is you got to think through, and that little poem helps sometimes. So I'm going to rinse with what I'm about to put in. And the other thing is, we saw earlier that, boy, it took very little of this. It took very little of this to fill up to the mark. So I'm good. Here we go. And now I'm ready. I can mark this. So that's it. If it was 1 molar to begin with, it is now 1/10 of a molar, and that's just a generalization. When I go to do my data, I want to make sure I give all the significant digits. So let's talk about that real quick, but I'm going to clean off my glass right now so it's ready for a good run. So let's talk about significant digits. This is 10.00, right? We can think about this one. I now have measured 1 mil, then I got one more line, so I'm going to measure in 1.00. So this particular tool isn't very good for getting me, if I wanted 4 significant digits, I need a better tool. So this would be 1.00, and so that would control the significant figure, so I can't keep 4. So another plan would be to use a better tool this way. So this measures 1 mil in 1/100th. So this is even better. I get my other pipette, right? It fits on here. I can do a pre-rinse. I'm going to do that a little bit differently. Now, I missed this earlier, so I'm going to go through this again. Now, this glassware, I assumed it was clean earlier, but that's not always a good thing to do. So this is a great example. I am about to dilute a 1 to 10 in a 10 ml flask, and I'm going to dilute with water. So in this case, the solution is okay to wash with because I'm going to dilute with it anyway. This isn't the critical mark, so it's okay to rinse these out with water in that case. So here's the difference, right? I am going to dilute, right? So solvent is the root for rinsing. So here we go. I'm going to use the same principle. This uses so little fluid you can even pull that all the way up for a rinse. Which is kind of nice. Now I go past again. If I went right to the 1 mark and spit it out, or to the 0 mark and spit it all the way out, then I would be using that little that narrow part, and that's not consistent. So what I do is I go up past. This has a -1 mark on it. So I'll go right to that -1 mark. And that's great because you can see that fluid cleaning it out. Touch it off. Go right inside here. Make sure it drops in. And go right down to the 9, right? It's going to be on the 9 line. That way I go to a line. There's right to the line. I touch off the tip. Get rid of the waste. This one's gone. Here we go again. So now you see why it was okay to rinse with water, because I'm just going to put more water in anyway, right? Make sure I get close to the line. Here we go. I kept my water with my water here. That's good. Right to the line. Perfect. And, you know, just a note on these again, you know, sometimes you want to clean those off, but they should be cleaned beforehand. We're all right. 2, 3, 4, 5. Get a good circle in there and we're good. Here we go. So now, again, I don't need to use it all. It's done. And this one I'm going to call 0.1 high quality. There you go. All right, now here's another issue that comes up. So we solved it once where now we have our digits back. Because the way I would read this, every line here is 0.1, and then there's 10 between that, so it can actually read 0.10 with lines, so I get one more digit beyond that, so I added 1.0000. So I have 4 significant figures using this. I'm diluting it to 10.00, so that has 4 significant digits. So my new concentration literally has 4 significant digits in the answer. The other thing about dilution is, let's say that I want to get smaller than the 0.1. Now the problem is, if I'm not using the full 1, right, because I had 1.000, right, and I'm going to use something less, so let's just say I added 0.5 of this, I lost a significant digit. Because I would be adding, out of this volume, I would be adding 0.500. Now I'm back to 3 significant digits. So how do you get around that? Even though this is the best tool I have in the house, this is one of the smallest, there's a trick. It's called the dilution of dilutions. So if I take this high quality mix, which is already diluted, and I then repeat it again, and just go 1 to 10, right? Then it's going to be 0.01, but I'm going to have the same 4 significant digits. So that's the trick called dilution of dilutions. So now if I'll take something out of here, so again, I'm going to just do that just to prove the point. Again, I'm going to think about this. Okay, I'm going to dilute with water. So if I'm diluting with water, dilution, then solvent is the solution or the root. So that's okay. I get my new pipette. I take my high quality mix. I have plenty to spare even on the rinse. That's good stuff. Go to the 0.1 mark. Deliver to 9. There it is. And go to my waste. Go to mark with water. Make sure I rinse. On the side when I'm doing this. Okay. Sometimes it's really helpful to get that dropper right centered, because if you kind of surface tension will hang it up on the side sometimes. Okay, now again, if I have a little drips hanging up the sidewall above the line, I'll go in there with a little Kim wipe and grab those, because I don't want them mixing in and diluting above the line off the sidewall. By the way, if you have a lot of that, a lot of hanging up on the side, that just means your original volumetric flask was dirty. So if you clean a volumetric flask properly, it will literally, it won't have much hang on the glass. The glass is very clean, so it will release the fluids. And then another thing about that is you never dry these in an oven. So that's the other trick of this. So now what I've done, see what we got. Well, probably shouldn't work over the other samples because the minute I drop something in there, I ruined it all. Here we go, above the mark. Again, I don't have to fill very high. And this guy is 0.01. And we're off to the races. All right, so I'm not going to do a full calibration set, but you see what's involved. The other thing you always need for your calibration set is you need a blank. Blank is a solvent. I'll explain that here in a minute when we get back on the instrument. I rinse this with water a few times. And there we go. This is my blank. And I'm ready to go. You, of course, would have all the samples prepped up, but I just want to give you the general ideas. Let's jump over and look at the instrument for a minute, and I'm going to teach you the rest of that, and then let's start with the ocean optics, just because it's a little better quality. So, again, now what we're going to address first, this issue of there's different intensities at all the different energies. And so what we do is we basically say, okay, let's put it in the computer what all these marks are, but let's do that for when there's a what we call a blank in there. So I'm going to put the water in. Now the red tide runs this direction, the light runs this way, so I want to make sure my good glass is going this way. And then on this one, it runs the same direction. You can see I've got these organized the same way. All right, the main thing is, though, you don't want the optical glass turned 9 degrees as if it's reading that way. This is what's called the, and if you look, you can kind of get over this. This is they call it a relative reference. A lot of people would call that the blank. And so I'm going to click that. The reference has been taken. This is a light reader. This instrument literally reads light, correct? So there could be a problem with the lights in the room coming in and it reading those. So the way we take care of that is we actually turn off the light for a minute, and then we say, well, whatever you read at this point, we're going to ignore that from the spectrum, because that's what we call stray light. So when you look on the instrument, that's this little black bulb sitting over here. So we're going to click it. I'm going to put the water back in just to show you what's happening now. So what the instrument does now, mathematically, what it says, instead of reading the intensities at all those, it basically says, okay, whatever the intensity I read here is considered 100%. No matter where it falls, we call it 100%. So when you look, the main line across here is 100%. Now, this is a little above and below, and if you want, when you're here, you can actually update the blank again. You can just click it one more time, and that'll sometimes clean that up and put it right on the 100% line. So now we subtracted out the black. We're reading the water at every energy level along here. It says, okay, this is actually 100% instead of all the different intensities. Whatever that intensity is, they call that 100%. Now anything different than water must be sample. So that's why you have to have your solvent as the blank. And just so you may know, because a lot of people will be looking over here and they'll go, wait, what's this doing down here? It's just flipping up and down. That's your indicator that basically I can't read in that area. In other words, I'm looking at the extent of where this instrument actually is accurate. So the diodes down in this area are not working. And that's not a mistake, or it's not a problem with the instrument. You just have to get a different bulb and a different reader that could extend down, and that's the ultraviolet region. So there's nothing wrong with that as long as you see a nice flat 100%. Okay? Now we're reading this in percent transmittance. So that means 100% of the light is transmitting through, which it should, right, if you just have a blank in there. So now what I'm going to do is I'm going to flip over and I'm going to grab the mother solution, because that's the most concentrated, and that's a good one to take your a reference from. And sometimes when I look at these, if I see a little, this one had a little air bubble in it, so I kind of tapped it and that freed that bubble up. So I put that in, proper orientation. So now you can see the least transmittance is right around 800, and that is exactly where copper should be reading. So that has to be sampled. So the only thing that would absorb the light is the chemicals in there, and this is the signature for the copper, so this is where I'm going to read now. This one, when you say calibrate dark, it literally just turns off the light. Now the difference is it has an LED light, which is a little less, it gives you a little less intensity. This has like a standard fluorescent light, so that actually you need to leave it on the whole time. That's why we use a black box to block off the light. This one doesn't need a black box though. When you read the blank or the dark spectrum, it literally turns off the light. And it says you're performing calibration. So I'm going to go back over, show you the software again. So I'm going to take the dark reference, just click it, performing calibration. Now it's measured the dark. Then I put my water back in there, right? That's my blank. Might also call that the calibration reference. So I click it. Got it. All right, great. Now I can turn on the spectrum. We're going to read in transmittance. Now I can start reading in transmittance. It's actually reading the electronic noise, and that's okay. This would be kind of instructive, but see, I'm not reading from 0 to 100%. I'm just reading between 95.5 and 100, so I'm seeing all the electronic noise. That gives me a chance to show you what will happen if you can signal average a little bit. I'm going to put this at 10. Smoothing is the same thing with what we did before, and we called it a boxcar width. And this is interesting. This smoothing feature, not really great. But we'll see what happens. Now, let's put our mother solution in there. But again, you can see the quality in the spectrophotometer almost immediately. This has a little bit different feature. What you do is you drag that hand over, and you can set it in here if you want. There you go. So that most concentrated reads at 12.8% transmittance on this particular instrument. But again, what you want to do is leave it at 800. So now I'm going to change back out to the 0.1. Just to show you a reference. And there you go. And that reads about 87%. And then we'll drop down to our little 0.01. And that one reads nothing. And that's a good indicator of that shows you the quality of the spectrophotometer. Although it looked like it was having more response, it won't even pick up the 0.01. It calls it 100%. So the points are, again, smoothing scans the average, same thing as scans the average in boxcar width. It's just a feature to get rid of electronic noise. You have to identify the major peak of your substance. I might even read down here. That's more of the maximum, so I might even read this particular sample at 827. But the key is, once I lock in on that wavelength, I have to stay there for the rest of the experiment. this is instructive because you can click between modes on this one, so it's helpful to help you see this. This is transmittance mode. If I flip to absorbance, okay, it kind of flips the curve over and you see a normal up, rising peak. Now this is really important because I'm going to just show you something. In the English language, if I read this in transmittance, right, and I'd say, okay, I'm getting somewhere around 13% transmittance. That roughly 100 minus 13, right, that's about, what, 87% absorbance should be taking place. But when I flip to absorbance mode, I don't see 87%. What I see is 0.89. Absorbance is the negative log of the transmittance. So we'll do calculations with that in the lab. So that'll be very, very useful for you. Okay? So I think that kind of gets you oriented, and hopefully now you understand what the dark spectrum is to get rid of stray light from the outside source that could be read in the detector, not from the instrument itself, but from the bulbs above me. What the reference is, we got to make sure we know what the instrument reads at each wavelength before we put sample in there, and that's what the reference is for. Commonly you drop pure solvent in there, so that will be subtracted out when you do the calculation. Hope this helps. I hope you learned some good lab techniques, and I'll see you online.